So far, we focused on separations that involve gas-liquid systems. But commonly in your career, you will encounter sorts of systems in which there's a liquid-liquid equilibrium, all right, in which you have two different phases that are both liquids, but each of these phases have different compositions of the chemical species, all right? And so these sorts of systems are useful for also useful for separations. So it may also be used for separations. In fact, this type of separation is dominant in the pharmaceutical field, useful for pharmaceutics, right? Where the active pharmaceutical ingredient that you're maybe trying to purify is very sensitive to temperature. So you really don't want to rely on heating and melting or vaporizing things in order to purify your chemicals, all right? So which are sensitive to temperature. Right? In fact, this is a type of separation that is being used in order to prepare the COVID vaccine, all right, that's coming out this year. All right, and so when we have a liquid-liquid equilibrium, I kind of want to paint like the physical picture that we're thinking of. All right, so what we should consider is, let's consider we have two different types of liquids, right? Where one liquid is an oil and another liquid is water, right? Now, as you know, oil and water don't really like each other, right? In fact, oil and water don't really mix, okay? And so if you try to mix these two different things, you would end up with a system or a solution in which there are two distinct phases, one that's oil-rich and one that is water-rich. All right, so let's consider a system in which we're trying to mix oil and water, and the oil phase, let's say, contains some sort of chemical species, like a vaccine. So V for vaccine, right? Oops. All right, and so we did our chemical reaction, and it ended up with creating our vaccine that's in an oily phase. But when we deliver it to people, we don't want it to be in that oily phase. We want it to be in a watery phase. All right, and so what we do is we mix the two liquids together. Okay, and so instead of having two distinct liquids or two distinct systems, we now just have one phase, or one system with two different phases, oil phase and a water phase. Yeah. And so even though the vaccine was originally in the oil phase, let's say when we mix the two liquids together, the vaccine actually ends up preferring to be in the water phase. And so now we have three vaccine molecules there and one here. All right. And so this is basically the sort of concept in what people try to achieve with liquid-liquid separations. Is they have two different liquids in which there's a chemical species dominant in one of the liquids, and they mix all the liquids together in order to get that chemical species into a separate liquid. Okay? And so when we describe these sorts of systems, and let's say we're interested in the concentration of the V molecule in each of the phases, one way we could characterize this is by comparing the mole fractions of that V molecule to one another. Okay? So this is the mole fraction of the vaccine in the oil phase, and this is the mole fraction of the vaccine in the water phase. Okay? This ratio is what we call the partition coefficient. Okay? Partition coefficient. And so in this case, if we had a high K value, that would mean that our mole fraction of V in the oil phase is much larger than the mole fraction of V in the water phase. And if we had a very small partition coefficient, the opposite would be true. Now I want to point out how this definition of the partition coefficient we have here is very similar to what you have seen previously with gas and liquid systems, right? Where if we took a gas-liquid system and we took a ratio of the mole fractions, this gave us the volatility. Volatility for gas-liquid systems. Right? And so really, you can make an analogy between gas-liquid equilibrium and also liquid-liquid equilibrium, where for the liquid-liquid system, that ratio is the partition coefficient. And for the gas-liquid system, the alpha here is our volatility, but it's basically the same thing as a partition coefficient. Right? And so I think it's important to point out that analogy and how, these different concepts actually translate to across systems. All right. Some final things I'll say about liquid-liquid equilibrium is that, here I guess I was kind of considering a system in which we just had two liquid phases, but you could also consider systems in which you have more components as well. So you could also have ternary mixtures where all three components are partially miscible with one another. Okay. And these sort of partition coefficient, descriptions for characterizing our system, not only do they exist for liquid-liquid equilibrium, but you could also have similar concepts in solid-liquid equilibrium as well. So similar equilibrium equations for specifically crystallization and adsorption. So adsorption with a D, which means you're basically sticking on the surface of something.